previous video was deriving this formula here for volume as the integral of cross-sectional area. Let's, in this video, do a classic example of finding cross-sectional area. Let's do calculating the volume of a pyramid of some given height and some given base. So what's going on here? Let's fill in some information. The base is a square of side 4m. So from there to there is 4, and also over there is 4. And the height, if I were to drop a perpendicular from the very midpoint of the base of the pyramid and connect the apex of the pyramid down there, that would be 12. Okay, so we want to think about finding cross-sectional areas, and we're thinking of the horizontal axis. This is the y-axis, and so down here we're starting at y is equal to 0, and so we're ending at y is equal to 12 at the top. So we can already start to fill in a little bit of information here. We know our integral is going to be integral from 0 to 12 of a of y dy. Now our challenge is to figure out what is the cross-sectional area. Okay, so the next thing on the agenda is we have to find what is the cross-sectional area. And the thing to realize here, so I just drew a little cross-section here. The cross-sections are squares. And so let's say that S is the side right here. So our area is going to equal S squared. Okay, so now our job is to figure out what is S, the side length of our cross-section, in terms of A. A is going to move up and down, so how does S relate to A? And the way we're going to do that is we're going to do this using similar triangles. So I'm going to draw a triangle here, and in fact a couple of triangles. So one triangle, the big triangle, has the height here is going from the apex down to the point right in the middle of the base. Then the second side is going from the point right in the middle of the base to a point in the middle of one of the sides of the base. And then the hypotenuse is going from the apex down this side all the way to connect up there. Then, in order to have similar triangles, I'm going to draw another triangle here, where two of the sides are this to where the top to bottom intersects this square cross-section, and then one side there, and then the hypotenuse is going up there. So we pop out. It's a little bit hard to figure out what's going on in the picture now. So let's pop out that picture now, and let's see what's going on. So first thing, the height overall is 12 here. And this base down here, it's half of the side length of a square, so that's 2. This right here, that is half of a side length of a square, that's S over 2. And if we're thinking of y as running from here upwards, then if this is y, then this right here is 12 minus y. And so we've got all the information we need to set up similar triangles. So this side is to this side, that's looking at the big triangle here, as this side is to this side, looking at that smaller triangle. Writing that down in terms of equations here is that 12 divided by 2, oops, not 2, not S, is equal to 12 minus y over S over 2. And so this is an equation here that relates S and y together implicitly. If we move S over 2 to the other side, we would end up with S over 2 times 6. So that is 3S is equal to 12 minus y, or S is equal to 1/3 times 12 minus y. So now we have S in terms of y, the height here. So how do we finish things off, or at least finish off figuring out the area? The area in terms of y is S squared, so it's that squared, so 1/9 times 12 minus y squared. Okay, so at this point then, all we have to do is we've got our area function. We already said that we're integrating from 0 to 12. And so the volume of the pyramid is the integral from 0 to 12 of the area is the cross-section of 1/9 times 12 minus y squared dy. Okay, so at this point, in the interest of time, you can, I will leave evaluating this integral as an exercise for you. The best way to do it is a substitution. U is equal to 12 minus y. du is equal to minus dy, and you can go from there. And when you crunch out everything, you end up with 64 cubic meters is the volume of this pyramid. Now, so that finishes off the calculus part of this. It's worth noting that we actually can derive this using high school geometry formulas. So some of you might know that the volume of a pyramid is 1/3 times the area of the base times the height. And so in this case, it's 1/3. The area of the base was 4 times 4. So that's 16. And the height was 12. And so if you actually calculate out 1/3 times 16 times 12, you do in fact get 64 cubic meters. So our answer checks out.